All right. So shear stress. Stress isn't all it's cracked up to be sometimes. So the so the name of the game of today is um, if you look at this I-beam here, it's a concrete I-beam with some which called rebar sticking out of it. You'll note the place where it failed, which is in the center in what we call the web. Um, but that's not really where we'd expect it to fail, right? So if this is being put in bending, where would you expect the maximum stress to be? Say again? Okay, so be over here, and then where along the cross section would it be? Top and bottom, right? That's bending, right? However, this thing broke in the middle, which is where the minimum bending and stress is, which is weird. And this is what we're going to kind of look at today, because this is actually a failure in shear, which is also weird because shear stress is normally like vertical, right? Not horizontal. So we got some we got some stuff to look at today. So previously in ENGR315, we had a nice little three-point Hinman bending problem, right? And we could cut that out of cross section, find some shear loads, find some bending loads, right? So today I want to kind of step back from that a little bit and kind of look less in an aggregate and more of, okay, if I have this beam and I just look at one spot on the beam, like one little cube on the beam, if I cut that out, what's acting on it? And sure, there's some bending load here, right, that I'm not showing because there'd be a whole lot of errors here. So I'm looking at the shear load on one little chunk of that beam. And this is the same thing that we had before. You have some tau xy, some tau ix, some shear stress going on every face. We know that it has to be on every face because if you just had like the one on the right and the one on the left, I have sleeves so I can't like block them out appropriately. Sorry. If you just had this guy and this guy, one on the right and one on the left, you'd have this unbalanced moment. So you need to have the other two. Played with that one before. But that means that we have not only stresses going up and down, we have stresses going left and right too. And that's where these crazy horizontal cracks effects come from. So how do we start to compute? So if we look at how we start computing this, the idea is kind of similar to when we were computing bending stress. We know that for an element on the cross section, we need to be in static equilibrium. So if I cut things out, I can kind of start to throw some concepts together and maybe we can make an equation. So let's break this thing down. So this is just an element sitting on the beam. I'm just looking at this little bit here. We're in three-point bending, so we have some set of normal stress distributions that are acting on this little element. Will the bending stress be the same on either side of the element?
Yes.
Why? Okay, I heard yes and no. Why? Both. Why yes?
If the load is on top of it.
Okay. Okay, if load is on top of it, the bending stress will be the same because if you, and you're saying that, I'm guessing, because if you look at your shear and bending moment diagram, wow, that's a terrible line, for 3-point bending, it ends up being something like that, right? Around the center of the beam. Is that kind of what you're saying?
Yeah.
Okay, that's true, but that's only true at the center. We are not at the center. So is the bending, so is the normal stress from bending the same on each side of the element? No, right, because the bending moment's going to be different on either side. If the element has some finite width dx, even if it's an infinitesimally small dx, hex in the elements say like here, over the width of that element, it's really hard to draw when you can't do that. Over the width of that element, the bending stress is going to change by some amount. So these two stress distributions are not going to be equal to one another. However, the element still needs to be in static equilibrium, right? That is always true, unless like part of the beam's going to like be shooting off somewhere. It has to be in static equilibrium. So if we just looked at bending stress, we wouldn't be there. But that's not the stresses and the forces from bending aren't the only forces acting on this element. Like we were just saying, we also have some shear stress acting in the horizontal direction, right? Does that give us a force horizontally?
Yes.
Why? And if you say it's because it's marked on the PowerPoint, that is incorrect.
It was horizontal on the stress cube before?
Yeah, but so sure it's okay, but that was stress. Why does that give us a force?
Stress and force are usually in the same direction.
Usually, not only usually in the same direction, stress and force must be in the same direction, right? If you just think of it from the perspective of like just a basic average stress, stress is called proportional to force. Wherever you have this stress, there has to be some load creating that stress. You don't have a load, or you don't have any stress. You just have a beam that's floating in space. It's just hanging out there. It's not under any stress. So in this case, like you said, we have some shear stress in the horizontal direction. So that means that we have a force in the horizontal direction. So there. We're calling it delta H in this case. And between these three force distributions, be it from bending, because there's some normal stress, right? So if there's some normal stress, there has to be some normal force, right? So you have two normal force distributions, and you also have this horizontal shearing force, delta H. Between those three, that stress cube needs to be in static equilibrium. Or you can think of it as, I'm going to say, yeah, we'll just go with that for right now. So if I have that, let's do some, wow, this is really not working out too well. Let's do some summation of forces in, call this the x direction, or might say the axial direction. And if this keeps up, I'll just go back to a whiteboard. So what are the forces acting in the x direction? FA. Oh, what's FA? Stress A, yes. There is, but is it the same all the way across the element? Correct. So what do we have to do? distribute it, or integrate. Here, right? We want to add up all little force contributions across the edge of this element, and the way to do that's to integrate, right? And I can do it for sigma b too. And essentially that's integral sigma a times some differential area. So stress times area all the way, which call hold on each little step across that face. And sigma b is going in the opposite direction, so minus sigma b dA. Wow, this is pretty lousy. Come on, smartboard, you can do this. Okay. Minus some sigma b dA. Okay. So what other forces are acting here? Shear stress, right. So it's like a, wow, okay. We're just going to go with whiteboard here because that's not playing nice. So we have some summation, of force in the x direction, have integral of like sigma a dA minus the sigma b dA plus some delta h. Cool. But this doesn't really help us, right? Because sigma a and sigma b, oh yeah, this equals 0. They're not related to, it's not telling me something in terms of a value that I can compute, right? Like I can't just obtain stress by looking at a beam. I can obtain like moments and stuff, but not stress directly. And this is dA crap too. So what can I substitute in here, maybe? Where do I get bending stress from? M bend y over I. So if I know that my bending stress is essentially my over I, so bending moment times perpendicular distance from the neutral axis divided by second area moment of inertia. Call this, yeah, just leave it like that. Then I can substitute in for both of these guys. I have integral, what, ma y over I minus mby over I dA plus delta H equals 0. Okay, we're getting closer. What can I take? Can I take anything out of this integral? Y is not constant because we're going across the vertical direction. I definitely is constant. So that's a good thing.
For this,
Yeah.
y, is
Yes.
it of the whole thing, the whole equation? Is it just of the stress cube, or is it of the whole?
Just the stress cube.
So if it's squared, it'd be 0 out of 1.
So y is just a vertical coordinate. So how do I want to say this? So if I'm looking at, please work. So if I'm looking at my little stress cube, and I have some stress distribution on it, and I want to find the force produced at any point along this distribution, I'd say, okay, I'm going to look right here. And there's some local bending stress associated with that point and that y coordinate, right? So so it's called, so for some differential area and some y coordinate, I get some stress, and that gives me a force. Does that make more sense? Okay. Cool. Did everyone else follow up?
Yeah.
Okay. So the idea is just this is the process of integrating for stresses. And it's called integrals are your best friend because you can use them to add up contributions of some function. And here our function is bending stress, which varies with respect to y. So if we're integrating across some area, if you will, y going in that direction, y is not going to be not going to be constant. If we're adding up all the contributions stacked up along that cube, along that element, cube, whatever you want to call it. All right. Yes.
Do we have bounds for our integral? Do we need bounds?
It's implied because you're integrating over the area that you're going to how do I want to say this? You're integrating over the entire area of the cube. If you're doing this analytically, you would probably break this down into a double integral. But most times that you see area integrals like this, it's at least in part conceptual. So you can kind of read this without having an explicit bound defined for it. Okay? Okay, cool. So we have all of this. Y is not constant. I is constant. Cool. And did I want to pull something else out there? Yes. Yeah, okay. And I can shorten that too, but one thing at a time. Okay, so I need more space. I'm going over here. Okay. That's plus x. Okay, so if I pull things out, so if I start pulling constants out of that integral, I got something like 1 over I integral. I'm going to shorten m. Actually, I'm going to pull that out first so you can see it. I can factor out a y from that ma minus mb thing, right? So if like a y, dA. And the ma minus mb, I'm going to shorten to dm. It's just some change in moment across the width of that element, all right? Plus delta h. Cool. All right. So if I have a dm, I think that you'd agree if I said that dm over dx times dx would be the same as dm, right? Those are the same things. It's kind of like multiplying by 1, but different, right? But fun thing is, dm dx, if actually I think I remarked on this before, but if you look at a shear and bending moment diagram, how is the bending moment diagram related to the shear force diagram? Mathematically speaking. Right. Hey, if I look at say this is my bending moment for 3-point bending, say it doesn't matter, it's just a convenient example. This is my shear force diagram. Shear is something like that, depending on how you choose your sign conventions. Bending's like that, which is suspiciously related in terms of the shear force being the derivative of the bending moment with respect to x. So that means if I can state this equality, I can also say, if I give myself some more room, I can also say that I'm going to call the shear force V, because that's what the book uses. I can also say that shear force times some differential length, which here is the width of her element, is equal to the change in bending moment across that element. It's almost like numeric voodoo, but different, because it actually works. So if I substitute that guy in, 1 over I integral v dx times y dA plus delta h equals 0. If V is my shear force, and that's just whatever force is acting on this cross section, is that constant? So if V is my shear force, and that's just whatever shear force is acting on this cross section, is that a constant? Yep. Dx, that's the width of my element. Is that a constant? So I can pop those out of the integral too. And that gives me something like v dx over I integral y dA plus delta h. Game on. Yes.
So for going back to the last one there,
Yes.
you then didn't do the first one on here.
Yes.
That's got a Y.
I factored out y, and then I combined ma. So the missing step here would be something like ma over I. Well, I factored out the I already. Be like 1 over I ma minus mb y dA plus.
You gotta check off the Y.
Well, the y is not going outside of the integral.
But it's the same for every integral.
Correct. Yeah. Yeah. I can pick the same y coordinate on each side of the on each side of the element. Yeah.
But it changes because Y. You said, okay, so like I understand that you can pick the same coordinates,
Yes.
but it's not constant because Y.
Oh, because I'm moving. Because in order to add up all the contributions from stress to a net horizontal force along the element, I need to move along the y direction. And so you might think, in order to integrate across the whole area, which is what we're doing here, I need to move in y. Yeah. Okay? Cool. So that's why y is not constant, but I can factor inside of an integral because math is cool. Yeah.
What is V again?
Say again?
What is V?
Shear force.
What's up, V?
It's the horizontal force from, or the horizontal force from shear. V is the vertical force from shear. Yeah. Yep. Okay. So, I got this together. Sweet. Okay. Sweet. Okay. So now I have this, which, well, we're getting somewhat closer, right? Because shear force, I can compute second area moment of inertia. I can compute dx. We'll get there. There's integral y dA thing. What does that look like? What's that similar to that you've already seen at least once? You guys remember an integral y squared dA? Okay. So the integral y squared dA, that was when we were dealing with the second moment of area. And that's like all this I stuff that we've been playing around with. So integral y squared dA is the second moment of area. Integral y dA is actually the first moment of area, which we're going to simplify as Q. big Q. Little q actually means something else if you read the book more. So be careful of that. But what the crap is that? So let's work with that one. All right. So for the first moment of area, integral YdA, Q, whatever you want to call it, is actually a lot more straightforward than you might think. So if you just look at the integral, it's y times the differential area. So if I have a box, say, there's my x-axis, there's my, well, to be consistent, that's my z-axis, that's my y-axis. If I had some differential area here, so I'll call it like this top bit, that's going to be my dA. The y location of that would be its centroid. So that's y dA, and which we call n, or a first moment of area. If I wanted to be more, if I wanted to do this integral out, what would I do is I'd actually determine what that dA is, what that differential area is. So say that this beam had a height of h/2, and it has a thickness of t. I'm going to say this. And let's say let's say that the distance to the bottom of that area is y. I'm deliberately choosing the bottom because it makes a lot of math more convenient. If I define it like this, how would I find the area of that portion of the cross section? It's kind of, yes. So I can kind of think of this as I'm going to say that's y bar now because my y is not going to the centroid. Okay, so like I'm going to say that the distance to the centroid is y bar, just because I have my things defined differently. So the dA would be what? h/2 minus y. So that gives me the height times t. Okay, what's y bar? Yep, but how can I express that in terms of y? Okay, so h/2 minus y, this y/2 or closed paren over 2? Okay. So if I do that, that gives me that little distance divided by 2. That gets me that height, right? But I need all the y. But I need all the y bar. So what else do I have to add to this? Plus y, right? So h/2 minus y, close paren, divide by 2, add y, multiplied by the expression for dA that we had in the last one, minus y times t. Game on. That's an expression for the first moment of area of some differential area on this rectangular section with in terms of y. Okay, that equals q. Well, actually, because we have, how do I want to say this? How do I want to say this? Because we've we've determined this explicitly without having integrate that equals Q. Sorry, this whole thing is Q right here. How do I say this? Because how do I say this? Instead of doing an area integral, we are working with finite areas instead of differential ones. So we kind of short circuited having to play with the integral. Sorry, I kind of smoothed over that. In a sense, we used the definition of the first moment of area, which is some distance of the centroid from an axis times a differential area, to construct a definition of what the first area moment of a particular shape is. Okay? H and y are not constant. Y is not constant. H, is that constant? Right, because it's a geometric length. It is defined as one number. Yeah. So this would be Q for a rectangular beam. But this is still a bit of a pain. This is still a bit of a pain in the butt because it's messy and long. But we'll get what's called a whole. But let's simplify this down. So if I take this first guy, kind of work the math out, I'll get something like h over 4 minus y over 2 plus y. That's multiplied by h over 2 minus y t. Simplify this further, h over 4 plus y over 2, h over 2 minus y t. And hey, look, if I pull a 1/2 out of this, those are like those like a conjugate pair, right? And if I FOIL that out, I get something like, and I'm going to bring the t up front. I get something like h squared over 4 minus y squared. So the value of the first area moment is actually a quadratic in y, which is interesting for us because if the value of q varies quadratically in y, that means that the value of this term also is going to vary quadratically in y, right? So, get rid of that outline. Actually, need space. All right, but we're not going to substitute that in quite yet because it's a big term and we have some more work to do yet. Because this still doesn't say anything. All that we've done in defining what the first area moment is and crunching an expression for that is saying I can compute q for any given y. I can find v, I can find I. The only question here is dx, and maybe I can choose to solve for my horizontal shear force. So let's try to solve this down a couple steps further and get it into something that we want, and then we'll start substituting crap in. All right? So, I'm going to erase stuff. Okay. So if I have, I'm just rewriting what I had done there, higher dx over I times q plus delta h equals 0. So if I have that, and let's solve for dh. So dh equals negative v dx q over I. Okay. However, I probably don't want a force, right? Like I care about stresses. Forces are cool, but only because they create stresses. So I want to divide by some area, right? Probably some like differential area, because that'll make a force into a stress. And in this case, if my force is oriented horizontally and it's a shear force, where does my area come from on this little differential element? What face am I trying to get the area of? The bottom, right? Which is going to be, what's the area going to be? Yeah, so dx times thickness. We kind of said the thickness we can call t. So I'm going to divide by 1 over dx times t. Say again? No, not necessarily. Dx is just some differential length. And t is a finite thickness. So if I do that, conveniently my dx cancels out. I'll hold it there. I don't have to worry about that. Ain't that nice? Delta H divided by T dx is a shear stress. So I still don't have to care about the actual value of dx, which is awesome. And I get something like VQ over IT. Bam. We got an expression for shear stress now. And for a rectangular cross section, we said that Q is this thing over here, T over 2 H squared over 4 minus y squared. So if I substitute that guy in, T over 2 H squared over 4 minus y squared, we get that our shear stress is actually distributed quadratically in y, which is pretty stinking cool. All right. Yeah. Now, how do I say this? Now, if I wanted to, I could run some numbers and figure out maxima and minima. How might I do that? I'm probably not going to walk through it here because I don't have time. But how do I find where, if there's some distribution of shear stress, how do I find where it's a maximum? Because that's what I care about, right? Set this equals to 0. Say again. I could test end points, and if I did that, I'd find that the shear stress is actually 0 at the top and at the bottom. Somewhere. How would I find where? Wrong. Analytical solution. How do you maximize a function? You could graph it, but it'd be longer. Take the derivative, set it equal to 0 is the easy way. So you take the derivative of this whole shish kebab with respect to y, because that's the value that it's changing in, right? Shear stress doesn't change. Second area moment of inertia doesn't change. Thickness doesn't change. H doesn't change. T doesn't change. The only thing that changes is y. The rest of them are geometric values that are constant. They do, as a matter of fact. In this case, anyhow. So I could do that, and my maximum would end up actually being dead center on the beam when y equals 0, which kind of makes sense, right? Because if y is h over 2, those are going to cancel out. That's going to be 0, and this whole shish kebab is going to go away. If y is 0, that means that this is being decreased by the least amount possible, which make this a maximum. All right. Only thing to note here is that in cases where T does not cancel out, the thickness is because it's the thickness at the bottom face of this particular stress element. If you're traveling down along the y-axis, this would be whatever your local thickness is. So if you had like an I-beam where thickness changes at different points, you'd also have to change the value of T to match that. All right? Cool. Or if I expanded this out and I had like V over 1/12, this would be TH cubed, T times T over 2, H squared over 4 minus Y squared. I'd still have, what's called, so this T would be local, okay? So I still have a T in the equation. Okay. All right, so if I, so if I plotted it, again, it looks something like that. If you're plotting shear stress is coming out of the beam. It still is oriented in the ways that we've been talking about, but it's easiest to plot it like this. So hopefully that's not more confusing. And like I was saying with local thicknesses being what you use, that also who ends up giving you some interesting results for things like I-beams. So if you remember, the I-beam from the beginning of the presentation was cracked in the middle, right? Because for I-beams, that's actually where all this shear stress is concentrated. So that's pretty much that. Are there any questions on shear stress?
When we went from this, like, when we multiplied by 1 over dx times t,
Yep.
and it was like delta h, and that became t,
Mm-hmm.
can you explain how that goes to t?
It's a force divided by an area. So that's the definition of shear stress. Yeah. Yep. Any other questions? Cool. That's all I got for today. Thanks for coming by.